Alright folks, so today we're going to go through universal gravitation notes. So this is going to have some example problems in it, and one thing you will probably notice about our focus on universal gravitation is that this will also focus a little bit on history, so some of the people who contributed to the modern model of our solar system, maybe some discoveries, famous constants and equations and things like that. So to get started, we're going to go back and look at some of the earliest thoughts or predictions or theories about how things in space operated. How did they work? You know, where was the Earth? Where was the Sun? Planets that orbit around it? What were all of these objects that people stared at the night sky and actually observed? Because for many years, and going back in history, I mean, within the past 500 years even, there was a dramatically different outlook on what the solar system looked like or what space was. You know, the nature of what is a star, what is a planet. There really wasn't much of a discrepancy maybe between the two to some extent, or especially knowing exactly what they were. So we'll talk a little bit about the model of the solar system and how it developed, and we'll go from there. So some of the earliest accepted models of the solar system would have come from Claudius Ptolemy. And Claudius Ptolemy was a philosopher, mathematician, about the mid-1500s, and he had made a prediction that, he believed when he looked up at the night sky, the Earth would have been stationary in the center of our solar system, and around us orbited some of these things they've seen on a regular basis. Obviously, you see the sun and the moon in here, which has been observed for a very long time, and then also had some of these other larger, we call them planets today. At the time they didn't call them planets, they just thought they were larger stars or more sufficient stars, because these actually appeared to move around, where your typical stars in the night sky, they move throughout the hours, but their location relative to each other typically doesn't move, certainly not much. So this is kind of what they had for some of the first predictions of how the solar system operated. So we're going to just state a couple of the major things that were correct or incorrect about the model. Some of the biggest things that was wrong with this model is they had the Earth in the center, and this Earth-centered idea, again, was accepted for quite a long time. There were some other people in the mid-1500s who had other ideas, but it wasn't very highly accepted, because just naturally standing on Earth or looking into the sky, it's perceived that we are motionless, and when you see stars and the sun and the moon, they appear to move around us, where nobody quite thought or had the idea that potentially we're the ones moving or rotating around. They didn't know that the Earth rotated, and that's why the sun went up or down, because we either face it or face away from it. On every 24 hours we spin around on our axis on Earth. They didn't know that that was the case, so the logical thing to consider is, hey, I'm standing here, I don't feel like I'm moving, and everything's moving around me. So that was their first common thought. So this Earth-centered idea is also known as geocentric models. So geocentric means Earth-centered. So what is wrong about this model? Well, it's definitely missing some planets. If you guys take a look, compared to what we have today, there's definitely less planets listed here. They did have Mercury and Venus and Earth, of course, if you see where it is, Mars, Saturn, Jupiter, but you don't. What was correct about this model? Well, there was a couple of things, not a ton, but we do know that the moon orbits the Earth, and that is definitely correct. And it did have the identification of some planets. Other than that, there really wasn't a whole lot about this that was truly correct, but it was certainly a good start. Now, if we cruise ahead not too much further than this, in the mid-1500s there was a Polish astronomer. His name was Nicholas Copernicus, and he had a different idea about the location of the sun and maybe how the planets moved. He didn't have quite as much data collected as some other astronomers, and his ideas definitely were not accepted by people of high power. So back in those days, to speak freely wasn't always accepted, and the general public maybe couldn't make a consensus on it. So if you published a book or had ideas, it could quite easily be banished from, whoever your ruler was at the time, and that's kind of what happened to Copernicus. So, but he did have a different idea about how things worked. He was the first person to believe that the sun was actually in the center, and the sun-centered model is known as heliocentric. And though he never really had any hard evidence of this, no math to prove it or theories to prove it, nor was he really allowed to propose his idea out loud a whole lot. Most people thought it was just kind of foolish talk, and nobody really thought much of it. But years later, approximately 50 years later, early 1600s, his idea actually gets proved correct, which is kind of neat. Unfortunately, he was no longer alive. Copernicus is no longer alive at that time, so he didn't really get to see that, which is unfortunate. But that's how things go in science. Sometimes you may have collected information or made a prediction or a theory, and it might not be accepted or anyone's able to prove it until years later. And that's kind of what happened with Copernicus. By the late 1500s into the early 1600s, there were two famous astronomers, and there's different variations on how his name's pronounced. I say Tycho Brahe, some say Tycho Brahe. I'll call him Tycho. Tycho Brahe was basically the rock star of astronomers from any time in the past 500 years, just because of how widely he was accepted, how much money he was given. He had his own island, castle, the best optical instruments of the time, just quite unbelievable when it comes to that. And his vast collection of data, positioning of planets and stars and constellations and timelines was just quite unbelievable for the time. And he had, with his data collection, he had formulated a different idea or a model of the solar system, which they called the Tychonian system, and it was accepted for the most part by more people than say the Ptolemy system, or later on here we'll talk about Kepler, which becomes kind of full circle with it all. But his model here, it's interesting. It's kind of a little bit of a combination from the Ptolemy system. He still believes that the Earth is in the center and the moon goes around the Earth, but he does believe that all the other planets that we know of at the time orbit the sun. So kind of a goofy thought. If you could take the Earth out of its location in our orbit around the sun, he believed, Mercury and Venus were orbiting the sun, Mars orbits the sun, Jupiter and Saturn orbit the sun, but then we're still over here, and the sun goes around us while the planets orbit it. What's wrong with this model? It is still Earth-centered, which is the geocentric idea, so they were still stuck on this. And again, these are things that are incorrect about the model. Other things that are incorrect, it's still missing planets. And what are some of the things that are correct about the Tychonian system? Well, he did have some planets orbiting the sun. Maybe not all of them, but he did have some planets orbiting the sun. Some of the planets orbited the sun. The one planet he was forgetting was Earth, so they didn't. A lot of people didn't consider those other planets, or how they get their name was the wanderers, because planets translated basically meant wandering stars, and they did not consider the Earth to be one of those so-called planets. So
that part was correct.
Flip the page, look at the next side of the notes here. One of the most famous, well, at this point especially probably the most famous astronomer, or had the largest contribution to how the model of our solar system worked, was actually an assistant for Tycho Brahe sometime mid through his career, and his name is Johannes Kepler. Kepler was hired just to be a mathematician for Tycho Brahe, and Tycho was kind of domineering and somewhat of a strong soul, didn't really care to take other people's opinions, and Kepler had different ideas about how he thought this model worked. He didn't truly believe that Tycho was correct. However, he was hired by Tycho to do mathematical equations and to keep his job and make some money. That's what he did. However, when Tycho got sick and died, and if you want to look at a good story, look into the life of Tycho Brahe and how they potentially think he died, and/or conspiracy theories on maybe how the relationship between Kepler and Brahe ended. But when Tycho Brahe was dying, he tried to convince Kepler to carry on his work and prove all of his ideas correct, but Kepler was unable to keep that promise because he didn't believe the same idea of the motion of the planets as Tycho. So what happens after Tycho dies is Johannes Kepler has access to all this awesome knowledge, and he formulates some of his own ideas of how the planets move, and these are kind of the core basis on how we base most of universal gravitation. This is probably some of the biggest findings, and we end up with Kepler's 3 laws of planetary motion, and they go something like this. So these are unknown, nobody else had made any of these predictions, and they're very helpful here in the future. So for number 1, the idea or concept that planets travel in elliptical orbits. All of the other astronomers believe that planets went in perfect circles. So if you did look at the model of a solar system, the planets are close to perfect circles, but they definitely are not perfect circles. And an ellipse, if you look at what an elliptical orbit is, an ellipse is basically an oval. So if you could place the sun, not necessarily in the center of this, but they do say that ellipses have 2 centers. They have 2 foci, or 2 points from which you could draw distances to any outer edge between there and the foci, and you're always going to get the same distance. So kind of like a circle has a radius, which is a consistent distance from the center. The distance between the foci and out to any point on the edge of the ellipse, if you added up all those distances or had it as one distance, it would be the same. It would be consistent all the way around. So extremely important, and it kind of translates down into the next 2, where number 2 is saying that the radius from the sun sweeps out equal areas in equal time intervals. So the only way for that really to be possible, and we'll look at this more closely in a different diagram, is that when planets are close to the sun, so Mercury and Venus, are closer than the Earth, they travel very fast relative to the Earth. The closer they are, the stronger the gravitational attraction. Hence, to keep things in balance, they need a greater centrifugal force to be pushing them out or pulling them in, vice versa, to keep in balance. So they have to go faster. If their radius gets smaller and their velocity goes up, that's the only thing that they have, because the gravity itself gets stronger. However, planets that are far away, if you looked at Mercury, planets that are far away, such as Mars and Jupiter and Saturn and Uranus, Neptune, and any other maybe potentially comets and things like that, when they're far away, they're actually going to travel very slowly. So they have changing speeds or variable speeds, which no one else predicted either. They said, okay, well, some move faster than others, but they didn't accurately measure or even make the prediction that maybe they went faster and slower during different times of the year, which they do. The Earth and don't think of the seasons to have anything to do with being close or far from the sun. It's all the angle that the sun hits us. It's the angle, basically the flux or the amount of energy that can come through any bit of surface area. However, we do get closer and further from the sun a little bit, and our speed of our orbit changes just a little bit also. And then Kepler's 3rd law. This is probably a harder one to understand, but in the world of mathematics, when they actually go to apply some of Kepler's laws, this is the one that was used to make predictions of some of the newer planets, such as Neptune and Uranus. They knew that there was other ones there, or if they were going to be there, when and where they should be looking. And this is kind of the basis on how it was set up. For distance away, he knew that there was some constant there. And a variation on this equation is to say that the period for planet A squared divided by the period of planet B squared is equal to the distance of planet A cubed divided by the distance of planet B cubed. So the application of this could help us predict, if the Earth goes around in 365 days, or say 1 calendar year, if we knew how far away another planet was, or if we knew the time it took for them to orbit, we should be able to figure out the distance, or whatever one is the unknown. And that's a lot of what they did to try to figure distances to planets was more based on their time than necessarily just observation. So 5 and 6, what is the difference in the beliefs about planetary motion from Kepler's point of view compared to other early astronomers? Well, the 2 biggest things, the 2 largest things, would be the elliptical orbits, and also, aside from elliptical orbits, came the changing, the variable speed, so the change in speed. Those were definitely new. And then the biggest thing also is, why did people more or so easily, not everyone, not super easy, but why were his ideas more easily accepted? Because he had the math to prove it.
He could make predictions. He could tell people, look at this, watch this, and everything would work out. Which is pretty amazing.
So, flipping to the next page, this is a diagram that's going to talk a lot about how they grew, how other astronomers and mathematicians or physicists kind of grew on the idea of Kepler. So there were quite a few years went by that they could use Kepler's prediction concepts or ideas. So in a model such as this, the diagram is supposed to be showing how planets can sweep out equal areas in equal times. So basically, assume that any of these t's on the diagram are equal to a time of, say, 1 month. So in 1 month time, if a planet is relatively far from the sun, it'll travel this distance. Over here, you'll see, if we write this as being 1 month also, the velocity of the planet is decreased. It hasn't traveled quite as far, but it's further away from the planet. So if I took the area of this and the area of that and could somehow calculate how large that is, if it was equal times, 1 month and 1 month, and they were orbiting the same object, then they would sweep out equal areas in that amount of time. And same over here, if this was also 1 month worth of time, you can see that the velocity here that the planet travels upon, or how far it travels in that amount of time, over 1 month, it covers a greater distance, so that radius turned more, but it's a shorter distance overall. So whether you had this A or this A or this A, they have equal areas in equal time. So again, we got the 1 month, here is the application. It's going to sweep out equal areas in equal times. Again, that's just showing that this planet is going slow, and this planet over here would be going fast, or during this part of the orbit, even if this is the same planet, because again, the whole idea of them being elliptical is that they're not always the same distance, and then this velocity up here would be some sort of a medium velocity, something that they, it's increasing or decreasing in speed here, and it would be increasing in speed as we get to this point here. So Kepler's ideas of how planets moved were excellent and great and wonderful, but there was no explanation as to how or why things orbited the sun even. So Isaac Newton's idea of gravity, things being pulled or attracted toward mass, was very cutting edge. And what Newton proposed, or the idea that he came up with, is that planets or forces between any two masses were proportional, and in Newton's day, it just looked something like this. He used this as a proportional sign, m1, m2, divided by the radius squared. He believed that the force between any two objects was proportional to their masses multiplied by each other, divided by their distance squared. Now, he had no, he at the time had not calculated what this gravitational constant was, but he knew that there was some common relationship between them. So it was years later when Henry Cavendish actually did this experiment using some really large, dense spheres suspended from real thin wire and some mirrors. And if you ever want to look up the Cavendish experiment, it's really cool. Cavendish discovered what this proportional gravitational constant was. We were able to actually calculate in newtons what force would be applied between planets based upon their mass and based upon their distance. So we'll ask a couple of simple questions looking at this equation as a whole. And question number 7 is asking what would happen to the force between two objects if one of the masses was doubled, and what would happen to the force if the mass was tripled. So we're not looking to get a finite number or answer for this. We're looking at what would happen just in general. Would things get larger? Would they get smaller? So if your force is here, gravitational constant is a constant 6.67 times 10 to the negative 11th. So that number never changes. Now the mass, m1 and m2, could be a large object and a small object, two objects of the same size, whatever it may be. And then r squared is the distance squared between them. So if we were to double the mass of one of those items, what's going to happen to the force? Well, the force of gravity then would be multiplied by 2, because these are simply multiplied by each other. They're not squared, they're not square rooted. It's just kind of a linear relationship. Same idea if you triple the mass, well, the force of gravity now is going to be tripled. Now that doesn't hold true for changing distances, because the distance now is something that's divided, and not only is it divided, but it's divided by itself squared. If we take a distance and you double it, you have some value down here, that's twice as large as what it was before, and it's squared on top of it. So what would be happening to the force? Well, the force of gravity at that point then would be 1/4 of whatever it was before. So you only doubled the distance, but you're only getting 1/4, not a half. So a lot of people think, well, this is twice as large, I'm dividing by that. Why isn't it half? Because it's a half, 1/2 squared is a half of that squared. So a half times a half is a quarter. And same thing happens, well, what happens if the distance was quadrupled or multiplied by 4? You got 1/4 squared. That means all of a sudden that your gravitational force is going to be 1/16 of whatever it was before. So now we're going to actually try to apply some of the universal laws of, or the universal law of gravitation. So for this, you are going to need to know the large g, or the gravitational constant of g, the 6.67 times 10 to the negative 11th. And then they should give you some masses and they should give you some distances so we can calculate the force. So whenever you solve these problems, you're going to want to list variables and equations to see what it is that we're going to be using. Now, one thing to notice here, and I got a typo on my notes, but I believe in your notes it's correct. Your units for mass have to be in kilograms, and your units for distance need to be in meters. So if for some reason they give you a distance and it's in kilometers, you just have to make sure that you convert it to meters. Okay? Because notice the units for the gravitational constant is a Newton meter squared divided by a kilogram squared. So when you have two masses in kilograms on the top multiplied out, it cancels with the kilogram squared, and on the bottom you have a distance squared. If the distance is measured in meters, then it will cancel with our meters squared, and then you're left with just newtons. So we'll set the problem up, write out our equation. We know that f of g is equal to the big G times m1 m2 over r squared. Looks something like this. So let's plug in the values that we know. So setting this up may not be so difficult if we know exactly what each of the variables are, but it is common to find students who make mistakes actually multiplying these numbers out on a, multiplying them out on a scientific calculator and so forth. So if you're only using a phone as a calculator, I recommend maybe doing this in steps. If I go and plug the numbers on this, and you guys should check your answers here, attempt this to see what you get. I get about 2.00 times 10 to the negative 10th newtons. And when you look at this number, initially you might think it's big because there's a lot of numbers written there, but remember this is to the negative 10th power. This is a very, very, very small force. For example, number 11, so again, we'll list our equation. F of g is equal to the gravitational constant times mass 1, mass 2, so our two separate planets here, and then divided by their distance squared. So let's plug in the values that we get. So the results I get for this are 2.5 times 10 to the 21st newtons. So this is a much, much larger force than the one we had in the previous problem. Alright, the next set of examples that we're going to look at is going to be talking about how to calculate the velocity of planets or objects that orbit some other body. So commonly we'll talk about the sun being the central body and then the planets that orbit the sun, or maybe comets that orbit the sun at different locations. But this would also hold true for things that, say, orbit the Earth. So there's thousands and thousands of satellites that orbit the Earth on a daily basis. One of the largest satellites that we have up there is actually the International Space Station. So one of these examples that we'll talk about pertains to that. So as long as you know the gravitational constant, and then the large M that we have represented in this equation talks about the mass of the object that's being orbited. If you divide that by the radius from the center, and remember these distances are always from the center of the mass, if you square root that whole value, it will tell you the velocity that the object needs to be traveling. If you want to see how this is derived, certainly feel free to let me know. When we talked about circular motion and we talked about centripetal force, basically what we end up doing is we take mv squared over r, and we set it equal to this gravitational constant g m1 m2 over r. This is the equation for the centripetal force pulling an object around to keep it continuing turning in a circle, and this is the force of gravity pulling in. We just know that the centrifugal and the centripetal force of a planet in orbit has to be balanced in order for it to maintain its distance from whatever it's orbiting. So if the centripetal force is too great and it's pulling in, centripetal force is too great pulling in, the object's going to crash into whatever the object is. If the centrifugal force, the outward force is too great and the velocity gets too great and it pulls away from gravity, it's going to drift away and drift out of orbit. So planets that are orbiting in any sort of a pattern, the balance of the centripetal force, the gravitational force basically has to be constant. Take a look at example number 12. It's asking what is the velocity of Neptune as it orbits the Sun at a distance of 5.4 times 10 to the 12th meters from the Sun. Now, they don't give us the mass of Neptune and they don't have to, but we do need to know the mass of the Sun. So I did list some of that up here, and again, this large M is the mass of the center body orbited, typically the Sun. With our equation that we have given to us, we're going to have the gravitational constant, the mass of the Sun, divided by the distance that they are away. So let's plug in what we got. So just remember, when you're solving this, think of the square root as a grouping. So you have to find the number on the top and the bottom, divide, and then once you've divided those, then you can take the square root of everything that's underneath. So if you want to practice inputting this into your calculator, the result that you should get for your velocity here, 5,431 meters per second. So that is quite fast. If you even think of what the speed of sound is, the speed of sound is like 340 some meters per second. So it's going about 16 times faster than the speed of sound, so about Mach 16. So pretty quick. Does it make a sonic boom when it's in space? You might think so. However, the area or the space that the planets are traveling through doesn't have matter, so therefore it can't create a sound wave, therefore it cannot create a sonic boom. So kind of strange space facts there, but interesting to think about. So if we're going to solve, we'll list the equation that we got. Gravitational constant, 6.67 times 10 to the negative 11. And the mass that we're using now, again, is the mass of the Earth, because we're orbiting the Earth and not the Sun, times 10 to the 24th. And then divide that by the distance from the center of the Earth to the center of the International Space Station, which is 6.8 times 10 to the 6th meters. Then we need to square root the whole thing. So again, practice punching in these numbers. 6.6. You should get a velocity of 7,659 meters per second. And for number 14 here, we're going to actually figure out how fast this is moving in miles per hour. So just to put it into perspective, for problem 14, they say there's approximately 2.24 miles per hour for every single meter per second. So just for some fun here, let's just see how fast we're going to be going. If we take the 7,659 meters per second, and you want to multiply it by this 2.24, this gives me a velocity now of 17,156 miles per hour. That is extremely fast. And the last analogy here we're going to look at, there isn't a whole lot of math here to do, this is more kind of a conceptual thought. We'll talk a little bit about how gravity and the moon and tides are all related. So large bodies of water such as Lake Superior or the Great Lakes, there is actually a tide. There's a measurable tide, but it's not really significant for any of our daily lives and applications. But this is kind of what happens. The moon itself, just like any other object, between any two objects with mass, there's going to be gravitational force or pull. Now, the sun is obviously the largest body in our solar system, so it kind of is the dominator of gravity, but it is also quite a bit further away from us than the moon. So we know that the two variables for gravitational force are distance and mass. So during a new moon or a full moon, so this would be the phase of a new moon, and if we were all the way over here, it would be considered a full moon. And over here would be either first and last quarters, dependent on the direction of their location. We'd have a dark side over here and a dark side over here. So dependent on our observation of it, we'd be looking at first or last quarter. The strongest tides happen when we are in line with the sun and the moon, because now you have double the gravitational effect in a single plane. The thing to envision that's kind of difficult in these diagrams is you got to remember that the Earth rotates around every 24 hours. The moon in 24 hours only goes about 1/30th its way around the Earth, approximately. It's about 29 days for the moon to get all the way around, to orbit around. So in 1 day's time, the moon moves only a little bit, but the Earth rotates all the way around in 24 hours. So if you can see where the high and low tides are, we have a high tide, low tide, high tide, low tide. Typically all happens within a 24-hour period. So as the moon rotates and we still have high and low tides, we got high tides in between the moon and low tides here, but they're less significant because you don't have the magnifying effect of the sun's gravity and the moon's gravity in line with each other. So this again still goes around in 24 hours, and the moon only moves this short distance in 24 hours. So it takes about 29 days for that cycle to continually repeat itself. So that's basically the relationship between moons and phase changes. So for number 15, when they're asking during what phases of the moons do you expect to have the tides be the most dramatic, it would definitely be during new moons and full moons. Alright, so that mostly concludes everything for the gravitational notes. This information is something that you should hold on to. Hopefully you have these printed out and copied down. They will not be submitted, but they're a great resource for solving practice problems and or on quizzes. So with that, thank you very much. If you guys got questions, please feel free to contact me, and enjoy the rest of the week. Thank you.